Hello, and welcome to the first video on the novel fire debris application called Fire Debris Application, Peak Detection, and Compound Identification. My name is Michelle Corbley, and I will be narrating this video. First, I want to give a brief overview of what this talk is going to discuss. GCMS data from fire debris samples undergo an automated analysis for detecting peaks and identifying compounds using this application. The chromatographic peaks are automatically detected based on the second derivative of the chromatogram. This works for both the total ion chromatogram and the extracted ion profiles. The detected peaks are identified based on an automated search of a library of compounds that are often observed in ignitable liquids and substrate samples that are from partial burning and pyrolysis. Finally, the process was optimized based on detection and identification of the 5 major peaks in the ignitable liquid reference collection and the modified destructive distillation method burns samples in the substrate database. Visual detection of chromatographic peaks is a straightforward process. Deciding which peaks are significant is a bit more complicated, and depending on the application, quantitative or qualitative, estimated signal-to-noise ratios of 10:1 or 3:1 may be helpful. Allowing software to automatically detect peaks is another alternative, which detects all peaks that meet a specific criteria. Automated peak detection often uses the Savitsky-Golay algorithm. The chromatographic intensity, I, along the chromatogram is examined in sets of n points. The intensity of the n points are fitted to a polynomial in time of degree m. In the example shown here, sets of n equals 5 points are fitted to a degree m equals 3 polynomial. Once the coefficients a, b, and c are known, calculating the first, second, or higher derivative is simple. The procedure is to fit the first n points, where n is the number of points in the signal, and then slide 1 point to the right and continue the process. It is typical practice to make n an odd number and to approximate the derivative for the central point in each group of fitted points. This slide shows a short section of a chromatogram and the first and second derivatives calculated for the chromatographic section. On the right panel, the vertical red line shows how the zero crossing in the first derivative corresponds to the peak maximum in the chromatogram, and the minimum in the second derivative corresponds to the peak maximum. A common practice is to find all of the peaks as minima in the second derivative. Once the minima are determined, the minima with absolute intensities that exceed a prescribed number of standard deviations from the mean of the second derivative are designated as detected peaks. All others are not detected. In the second derivative, showing 2 dashed red lines, only one peak has sufficient intensity to be detected. This slide shows an example of the full total ion chromatogram for a ground truth fire debris sample. The image to the right shows the second derivative of the chromatogram and the detection lines at plus or minus x standard deviations from the mean intensity for the second derivative, where x is some number of standard deviations. Some peaks that are too weak to identify in the total ion chromatogram may be stronger in one of the extracted ion profiles, or EIPs. The same peak detection method can be applied to an EIP. Manually identifying the chemical compounds that contribute to or are responsible for a peak is typically done by selecting the mass spectrum from a single scan or by averaging mass scans across a peak, subtracting a background collected adjacent to the peak, and then searching for a match in a mass spectral database. This procedure, coupled with chemical knowledge, is a good way to identify compounds that are potentially contributing to a sample. However, the procedure is labor-intensive and would not allow the detection of all compounds from a library that were potentially present in a very large number of samples. To accomplish this task, we need to automate the task of compound identification and couple the process to automated peak detection as discussed in the previous section. Once a peak has been detected, shown by the red box, a data matrix D is generated by concatenating 11 mass scans centered at the peak maximum intensity. The library is evaluated to determine which library compounds have a retention time within a specific window around the center of the peak. The library compounds within the retention time window form a set of target factors that will be tested against the principal factors obtained by performing principal components analysis on D. The math is shown on the following slide. Note that some peaks may have several potential contributing compounds within the retention time window, and some peaks may only have one library compound or no library compounds within the retention time window. Those peaks with no corresponding library compounds will not be evaluated. Peaks with multiple library compounds in the window will be evaluated against the mass spectra for each of the compounds. Importantly, with this method, more than one compound may be associated with a single peak. Target factor analysis differs significantly from a standard mass spectral library search because 1. Background subtraction is not necessary due to the PCA step, and 2. The target factor analysis method is automated. This slide shows an example of a compound identification for the peak marked by the inverted red bracket. The matrix D is formed as described on the previous slide and then decomposed by PCA, and the required number of principal components that must be retained is determined by Malinowski's determination of rank by median absolute deviation, or DRMAD. The scores and eigenvectors for the retained components are in matrices R double dagger and C double dagger respectively. A transformation vector, T prime sub 1, is calculated as shown using a mass spectrum for one of the library compounds, denoted as C double bar. The final step is to then recover the spectrum that most closely represents / matches the target factor that was projected into the PC space. The recovered spectrum is denoted as C single bar. The target and recovered spectra are compared by Pearson product moment correlation. If the correlation is high, the target spectrum can be represented as a linear combination of the eigenvectors and is therefore a possible contributing spectrum to the data matrix D. In other words, C single bar can be achieved by an oblique rotation of the eigenvectors. The panel on the right shows the target and recovered mass spectra and the correlation for 3 compounds within the retention time window that had the highest correlation. In this work, a minimum correlation of 0.99 was required to identify a potential component. The identified peak at 4.92 minute retention time corresponds to toluene. Peak detection followed by compound identification can also be performed for any of the extracted ion profiles. The peaks detected in an EIP may have been too weak to detect in the TIC. This method adds potential detection of more peaks than simply examining the total ion chromatogram. When a peak is detected in an extracted ion profile, the target factor uses the entire mass spectrum and data matrix D is comprised of the full mass spectra across a peak, not just the ions that make up the extracted ion profile. Peak detection and identification, as described on the previous slides, must be optimized. Optimization was conducted by examining 3 parameters. Peak detection was optimized with respect to peak intensity by examining the minimum number of standard deviations away from the mean of the second derivative required to detect a peak. This is referred to as the peak Z, and 4 integer values ranging from 1 to 4 were examined. Identification of detected peaks was determined with respect to the allowed maximum retention time or retention index window around the library retention time / index. This parameter allows for some shift in retention and is referred to as the peak delta. 4 levels of peak delta were examined in the range of 20 to 50 retention index units. Finally, peak identification was also optimized based on the minimum Fisher Z, which is calculated from the correlation between the target vector and the returned vector after projecting the target vector into the PCA space derived from the 11 mass scans around a peak maximum. The Fisher Z was examined over 5 levels in the range from 1 to 2. All parameter combinations were examined, a total of 80 combinations, and the best set of parameters was selected based on the criteria explained on the next slide. Assessing the performance of the peak detection and identification method requires a set of ground truth data. This is data that is known to contain selected peaks in the presence of other interfering peaks. The data chosen to serve as the ground truth data in this work was the GCMS data for entries in the Ignitable Liquid Reference Collection and the Modified Destructive Distillation Method data from the Substrate database. The 5 major compounds from each database record were compared with the search results to determine the true positive rate, which are the compounds identified and known to be present, and the false positive rate, which are compounds identified as present that do not correspond to the identified major compounds. The best set of parameters from the 80 combinations examined corresponded to a peak delta of 50 retention index units, a Fisher Z of 1, which is a correlation of 0.985, and a peak Z of 1. The resulting composite true positive rate was 0.96, composite false positive rate was 1.9 times 10 to the negative third, and the composite ratio of true positive rate over false positive rate was 482. These parameter values are used to examine fire debris samples for the automated peak detection and identification. Peak detection and identification have been automated to assist the fire debris analyst in identifying important peaks and peak patterns. The computational method identifies compounds from a 295 compound library that are present in a fire debris sample. Peak detection and identification performance is good for a fully automated method, giving a 96% correct peak identification for compounds that were present in a ground truth dataset while maintaining a false detection rate below 1%. Thank you for your time. For more information on the novel fire debris application, as written by the contributing authors on this slide, please click on the links in the description below.